Hi, I'm Alexis, and today my group is going to be presenting our Project 2 presentation. Um, I'm doing this alongside Darren and Connor, and today our topic is going to be about ropes with mass. So to introduce this topic, today we're going to be stepping beyond our initial assumption that ropes are weightless. We're now going to look into the idea where ropes exhibit a constant linear mass density represented by lambda, while they're maintaining inextensibility. This shift prompts a reevaluation of scenarios we've once explored throughout our physics courses. For our project, we were looking at how different parts of our model change when ropes have this linear mass density. We will also then be looking at how this addition would affect real-world scenarios. As I said previously, throughout our physics courses, we've assumed that ropes are massless. This has simplified solving for different physics concepts, for example, tension or acceleration. We will now modify different parts of our previous physics model to let us solve situations that involve ropes with linear mass density. Before we get into that, let's look at what exactly linear mass density is. So like I mentioned before, linear mass density is going to be represented by lambda, and it's going to be equal to m over L, which is going to be mass divided by the length of the rope. And basically what this is saying is that the length we're dealing with is that length of the entire rope, and this is saying that the mass is going to be constant throughout that entire length. So now with that being said, let's look at what's going to change in our physics model. So when we're looking at rope tension, and previously with our massless ropes, the tension in a massless rope is always assumed to be constant throughout its length, as there's no mass weight to alter that tension. If you have a rope connecting two masses, say M1 and M2, the tension in the rope is going to be the same on both sides. And this can be written out that tension, like total tension, is equal to tensions of all of the ropes added together. Now, with mass, the tension in a rope with mass is constant throughout the length as long as the mass is linear. So in our case, we are dealing with a linear mass density, which means that the tension in our rope is still going to be constant. If we were dealing with a nonlinear mass, say the rope is more dense in one area than the other, then that may alter a constant tension because it's going to pull differently. And in that case, it may depend on the position along the rope due to its mass distribution. And with that being said, we can write out our tension as T equals our linear mass density times our length of the rope times G, and G in this case is going to be the acceleration due to gravity, which is equal to 9.81 meters per second squared. And now let's look at net force. For systems involving masses connected to ropes, with or without mass, we're always going to be looking back to our equation relating to Newton's second law. And that equation is that net force is equal to mass times acceleration. And now, if we want to alter that equation to include the length of our rope and its linear mass density, we can rewrite it to be that net force is equal to mass throughout the system plus the mass of the rope, which is going to be that length times lambda times acceleration. Now, if we want to look at energy, specifically kinetic energy, we know from previous that the equation for kinetic energy is that kinetic energy is equal to half mass times velocity squared, or speed. If we alter this equation for a rope with mass, we're simply going to be changing that m for mass to the mass of our rope. And so that's going to give us that kinetic energy is equal to half lambda times length times velocity squared.
All right, so I will be talking about how does this affect a real world situation. So for our situation, we chose to do it on a sled being pulled. So Consider a sled with mass m being pulled up with force F by a rope of length L and a linear mass density that is constant. Since the linear mass density is constant, however, the tension should remain constant as well. So what we are basically asking ourselves is what will be affected, and what we found is that the acceleration of the sled, since now we have to factor in the mass of the rope and the sled, will be affected. And just a side note is that the sled is being pulled across a frictionless surface. So, a continuation of the next slide. Uh, we have what I said earlier. We got sled mass is capital M, force pulled is capital F, linear mass density is lowercase lambda, and length of the rope is uppercase L. So, for our scenarios, a massless scenario, the acceleration of the sled in this massless rope system can be calculated using Newton's law, which is just force divided by mass, get acceleration. Pretty simple. But with the mass, the difference is it's still Newton's law, but you have to keep the mass of the rope in mind as well. So for this equation, it would be acceleration is equal to force divided by the mass plus the length times lambda, which is said down there, right here.
Now we're going to be talking about another real-world situation. Two masses on a massless pulley, which we've talked about before in studio and in class and in homeworks, I'm pretty sure. So in this situation, we're going to have the right mass with mass capital M and the left one with lowercase m. And we're going to be trying to find the acceleration, the linear acceleration of, I suppose, both masses, but they'll have opposite signs. But to find the acceleration of the right mass, capital M, we're going to take the force of the right mass, which is going to be the mass times the acceleration of gravity minus the mass of the other object, lowercase m times acceleration of gravity. We're going to add those or sum those up. We're going to divide it by the sum of both masses in the system. That's going to be capital and lowercase m. And when we subtract the force of gravity from the lesser mass from the greater mass, we're going to get the force, I suppose, of the entire system. And that's going to give us capital A. And now we're going to be talking about what happens if the string, or rather the rope, has a linear mass density. And when this happens, we're going to, of course, assume that it's going to be a constant linear mass density so that the calculation of tension is going to remain the same. However, what is impacted is how we calculate the masses and how gravity affects those masses so that the forces are going to be increased. And by doing that, we're basically going to be adding the masses of the rope with the masses of the objects that are strung to the rope. And let's take a look at the equation we have here, which is the mass of the capital M plus the linear mass density times L, which is the length of the rope on the right side. As we can see, there's only one arrow, so that's going to be 1L. And on the left side, there's two arrows, so that's going to be 2L. So as you can see in the equation, it's going to be the mass of the rope on the left side is going to be 2L times lambda, plus, and of course, plus the mass of the object that's strung to the rope. And we're going to basically combine that. And if we look at the other equation below it, it's going to be just the same equation but simplified, which is going to be gravity times m, capital M, minus lowercase m, minus L lambda. As we can see, the right side has 1L, the left side has 2L, and we're going to basically subtract it. And that what we're going to also have to add all the masses that we can get from the rope, which is going to be 3L plus 3L times lambda. That's going to be the mass of the entire rope. And that's how we're going to get the acceleration. However, we also have a special case. And this isn't really entirely realistic, but just bear with me. Imagine that the right rope has a linear mass density, or the entire rope has a linear mass density of 1 gram per meter, and that the right side has a length of 1 left side has a length of 2 meters. And our equation from the last slide, the middle one, if we just plug in all our numbers, we can ignore the denominator for now. If we plug in 2 grams for capital M, 1 gram for lowercase m, and just plug in lambda and L, we basically can see that the entire numerator basically adds up to 0. So in this special case, and in other cases, I suppose, if the mass of the rope is significant enough, it can actually result in the system having an entirely different acceleration. Our conclusion: assuming a constant mass density, the calculation for tension is not affected by a massive rope. However, in our research, we saw, of course, that the calculation for tension is dependent on the linear mass density and how it changes throughout the rope. However, what is affected throughout all situations is that the mass of the rope itself can impact how the forces change in the system. And here are citations. Thank you.